Okay, so in this video, I'm going to talk about trailing axle and its effect on steering. So this should be the last component of steering geometry that I cover. So just to recap, I've covered Ackerman, bump steer, and caster. Ackerman has an effect on how the car corners when there is little to zero left to right weight transfer. Bump steer affects how much more the outside steering knuckle turns into a corner as the suspension compresses under a lateral cornering load. Okay, caster affects the rate of camber change of the wheel as the car steers. Okay, and they each have a different effect on corner entry, mid corner, corner exit steering, straight line stability, and behavior over bumps. So the final one here is trailing axle. So what does trailing axle mean? Well, what it means is, quite literally, by how much does the actual wheel axle trail behind the axis of rotation of the steering knuckle. Okay, so here again I have in here a kingpin at the top of the knuckle, and then on this side there's a bottom kingpin. So that defines the axis of rotation of this steering knuckle. Okay, and this is what this particular steering knuckle defines what we would call an inline steering geometry. So the wheel axle is perfectly in line with the axis of rotation of the steering knuckle. Now, on the older RC10s, you were able to actually buy steering knuckles that had some amount of trailing axle. I believe RPM used to make those. You can also, I think Team Associated made them as well. On the modern B5 and T5 series of chassis from Team Associated, you can adjust with little inserts into the steering knuckle. You can adjust how much trailing axle you have, thereby changing by how much the wheel axle trails behind the axis of rotation of the steering knuckle. So what does it do? Well, in order to help illustrate this, I actually had to make a PowerPoint diagram to make everything a little bit more clear. So let's imagine that this big circle here is my hinge pin around which the steering knuckle rotates. So this is my axis of rotation, okay? And then this big rectangle here is my steering knuckle, okay? And then this little dot here is the steering link ball stud, this guy right here, okay? And then within this rectangle, I have two extreme cases, the dark case and the light case. So in this dark case, I have a rectangle extending outwards that represents an inline wheel axle, okay? So that would be like what we have here. And then in this case, I have an extreme trailing axle scenario where the wheel axle trails significantly behind the axis of rotation. So that would be like taking this wheel axle and moving it all the way back here. Okay, suppose that we can magically do that. So we take this, and I just take this figure and I copy and paste it and just rotate it around this axis of rotation, and we can see what happens to the wheel axle in either case for inline and trailing axle, okay? And I just did it for the left and right sides of the car. And we can then trace out the arc that either of the inline or trailing axle wheel axles follows under the same exact steering input, okay? So what we see here is that for the inline steering geometry, the wheel axle covers a relatively sharp arc, okay? Whereas for the trailing axle, the axle covers a much wider and smoother arc. So what this basically means is that if I have an inline steering geometry, the steering response will be much sharper than if I have a trailing axle steering geometry. With a trailing axle, I can dull out the steering response. So if I want the car to maybe not be so twitchy, I might use a trailing axle steering geometry. Okay, well, we understand that with caster, when we use a reduced caster angle, that gives us a lot of steering grip on initial corner entry, but it also makes the car rather unstable going on straights because it makes the car very twitchy. So if I run a low caster angle, then I would tend to want to run some amount of trailing axle steering geometry to help calm the car down while cornering, while going in a straight line. Okay, and I don't necessarily lose out on the cornering grip on corner entry. I'm just using a trailing axle geometry to make the car more manageable going down straightaways. If I have to make minor corrections to the steering, the car's not going to, jolt to one direction or the other. It stays more or less in a straight line with a trailing axle geometry than it would with an inline axle. So it's less twitchy. So if I run low caster angle and or low kick-up on the arms, which also reduces the static caster of the steering knuckle, I would want to couple that with an increased trailing axle in order to keep the straight line stability about the same. And so then all I'm really modulating in that case when I combine those two together is how much corner entry grip do I have versus mid-corner grip. Because again, with a low caster angle, the wheel has a perfect contact patch to the ground on initial corner entry. And then as the car corners and experiences a cornering load, then the wheel cambers over and I lose mid-corner grip. Likewise, if I run a larger caster angle, okay, that makes the car already fairly stable going on in a straight line. But I might want to use a more inline steering geometry to make the steering response more aggressive. So that way I can basically get more or less the same total steering response as I would have with a low caster, high trailing axle geometry. Okay, so those two kind of track inversely with each other. Yeah, so that's what trailing axle does, and I hope that this helps to helps you understand how it works. It took me a little bit of time to figure this out, but making this type of a drawing really helped. Yeah, so that should cover it for all of the steering geometry components. And if you have any questions, of course, post your comments in the comment section, and I'll do my best to answer them. So thanks for watching.